So we're now going to continue our discussion on synchronizers in Java, kind of bouncing back from coverage of multi-threading and thread pools and so on. And we're going to begin with the coverage of Java ReentrantLock. And we're going to first start out by discussing the concepts of mutual exclusion in concurrent programs. And that's a very important concept. It's kind of at the heart of a lot of the synchronizers that are available in Java. And we'll also discuss a human known use of mutual exclusion, which is something I mentioned before, but we'll kind of walk through the protocol in a little bit more detail. So a mutual exclusion lock, otherwise known as a mutex, is used to define a so-called critical section. And a critical section is a group of instructions or a region of code that must execute atomically, otherwise bad things will happen. So the way that a mutex works, it is if you follow the protocol, and all the threads that are involved in this have to follow the protocol, it ensures that only one thread can run in a block of code in the critical section at a time. And the way it works is the thread shows up, it then attempts to acquire the lock. Now, if there's nobody else who holds the lock, then the thread that wants to acquire the lock will indeed acquire the lock. So it acquires the lock, and it will enter the critical section. Once it's in the critical section, it can run without fear of other threads corrupting the shared mutable state that is typically what is being either read from or written to in the context of the critical section. So a critical section is a place where shared mutable state or shared mutable data will be modified or read. While the thread that owns the lock is running in the critical section, any other threads that want to get into the critical section are kept at bay because they also have to follow the protocol and they have to try to acquire the lock. And the whole point of this is to prevent corruption of shared mutable state that could otherwise be set and get by concurrent operations. Remember, we don't want to have these race conditions that occur when multiple threads are trying to occupy the same memory space at the same time, where chaos and insanity and large legal bills are racked up when you do things like that. Now, crucially important to understanding how this all works is that other threads must also obey the locking protocol or bad things will happen. If other threads come along and try to sneak in without trying to acquire the lock first, then of course we're going to have problems. And this is one reason why it's usually best to encapsulate critical sections within a higher level pattern called the monitor object pattern. And we will talk about monitor object later. You typically want to hide this stuff behind some kind of method-oriented interface. You can use locks, naked locks, if you will, but it's usually better if you hide them because that way it's harder for people to do dumb things. And if it was the case that multiple threads were indeed running in the critical section at the same time, then bad things will happen, and that would induce a race condition, which, as you probably recall, is something that occurs when a program depends on the sequence or timing of threads in order for it to operate properly. And if that's the case, you're going to end up with race conditions. And race conditions have the nasty habit of manifesting themselves at the most inopportune of times. Usually when your program is about to do something important for a customer or some mission-critical operation, and then it goes awry and bad things occur. I used to joke back in the day when we didn't have many multi-core processors, and I would say that the difference between a concurrent program and the difference between a program that ran on one core with multiple threads versus multiple threads with multiple cores was that the multiple threads, multiple core version would reveal the bugs in your code much faster than the single core version, because sometimes when you have a single core, you don't get race conditions because there isn't necessarily all these issues with caching and other synchronization hazards. But when you run on a multi-core processor, it becomes painfully obvious that the problems exist. So just something to keep in mind. When a thread is done, it leaves the critical section, and it has to do something on the way. It has to release the lock, and that's why we always talk about putting the unlock calls in the finally block, so that that lock always gets released, even if exceptions are thrown or you return from some strange place that otherwise would thwart the normal exiting flow of control. And once you leave the critical section, then another thread can come along and acquire the lock and get in and do its thing. So some other thread will get a chance to, some waiter thread that's waiting will get a chance to come in. And the order in which things are released, the order in which the waiting threads are given access to the critical section depends on the semantics of the lock, and we'll talk about that later. So sometimes you can have fair semantics, which means the order in which the threads get access to the critical section is a function of the order in which they show up. That's the FIFO version. That's called fair. And there's also other ones that are non-fair, which just says whoever happens to be around at that point in the operating system or the scheduler decides to run it, that one gets to go. And we'll talk a lot about fair versus non-fair. In fact, that discussion is actually quite similar to discussions we've also had about semaphores. This thread that comes in, and the next thread that comes into the critical section, will also, of course, have exclusive access to shared mutable state, just like the one that came before it did. And, of course, other threads are going to have to wait until this thread is done doing its business. Mutexes are typically implemented in hardware using atomic operations. Remember, we talked about atomic operations before, and I talked about things like test and set and compare and swap and so on. And so that's typically how a mutex is implemented. And we'll talk a bit about mutex implementation later. It's some interesting subtleties in some of the cases. Recall that an atomic operation will appear to occur instantaneously and will either change the state of the system successfully or have no effect at all. So that's what it means to be atomic. So we've talked about that before with like transporter beams and Star Trek and so on. Under the hood, in Java, in the Java execution environment, Java virtual machine and so on, the mutex mechanisms are implemented ultimately by compare and swap methods, either in the Java unsafe class or other stuff that's similar to that. Let's talk briefly about a human-known use of mutual exclusion and mutual exclusion locks and mutual exclusion protocol. And of course, that would be the protocol for getting access to the restroom in an airplane. If you've ever flown in an airplane and had to go to the restroom, you probably have seen this kind of a scenario and this kind of a protocol. So the way it works is a person can only go into the restroom when it's vacant, which means that nobody's in it or it's unlocked. So you come along, if the sign says vacant, then you can come in and then you slide the door handle to the left or the right or whichever way it works, and it changes the state to occupied. So you atomically enter and lock the door. Now you're in the restroom. Anybody else who wants to use the restroom have to wait. And remember, on modern airplanes, you can't queue up to the front restroom. You can only queue up to the back one due to FAA restrictions because of 9/11. When you're finished, then you come out, you unlock the door, the state goes from occupied to vacant. And notice that this particular protocol is fully bracketed. The person who locks the door must be the person who unlocks it, unless you faint and then they have to come in and like pry you out with a crowbar or something like that. But we're not dealing with that use case. We're dealing with the normal use case. And at that point, whoever's waiting next can notice that the sign is vacant and they will go in. And typically it's a FIFO model in the sense that you wait in a line. But of course, if there's somebody in the line with like a crying baby, maybe you let them go ahead, right? So it's not always guaranteed to be FIFO in an airplane, just like it is not always guaranteed to be FIFO when you deal with computer systems too. So that's the end of the introduction to Java ReentrantLock. You really see we haven't talked at all about ReentrantLock yet. I've just talked about what a mutex is conceptually, and then kind of walked you through what a critical section is, how a mutex can be used to mediate access to which thread, because there's just one that can be in a critical section at a time. And we will come, and then we also talk briefly about the human use. The next part of the lesson will go into more detail about ReentrantLock.